Okay, thanks. Um, can I verify? Can I just confirm that this hand-drawn slide that I think is showing to everyone is actually showing to everyone?
Good.
Okay,
Yes.
great. Yeah. So thank you for the invitation to give this talk or lecture, and thanks to everyone in the audience who has shown up. I'm a professor in the Mathematical Institute here, so I'm sort of a physicist. My PhD was in physics, but now I'm some sort of hybrid of a physicist and a mathematician, so I'm maybe an outsider giving this talk. And this is a big subject. I teach or at least until this year, I was lecturing the first of the string theory courses on the M-Math Phys program. So I've been teaching a lot of string theory over the past few years, but it's a challenging, to me, topic to present to a sort of mixed audience. I don't want to assume that people know a lot about the subject, but there's certainly a lot of popular science material about string theory out there. So some people might already have a lot of opinions. And to people who've read a lot about string theory, reading books by people like Brian Greene and Mikio Kaku and Lenny Susskind and other people, I apologize. I'm probably going to end up saying some things that you've heard before because I really couldn't bring myself to demand too much technical material from people. But hopefully there will still be something useful to get out of hearing someone say it all out loud and be excited about various parts and less excited about other parts. Right. So I said in my talk description I was gonna sort of have a first half and a second half, and I think it's more likely to be a first 2/3 and a last third. So I want to begin. See if my slides work. I'm going to begin by giving what's going to be more of a sort of general overview of what I think are useful things to know about string theory, ways of thinking about it, how the theory has developed over time to a certain extent. And then in the last third, I'm going to try to say something maybe a bit more specialized in the sense that I'm going to make some points that I think are particularly interesting to me and hopefully interesting to you, people who are watching as well. But it's going to be sort of more specified to my own interests. So I'm going to start with some sort of basics, and really I'm going to start with a little bit of history, because I think the way that string theory sort of arose on the scene of theoretical physics is interesting and worth knowing a little bit about, although I'm going to not do justice to the history of it in this short amount of time. So the context for the birth of string theory, as it were, and I have a book called The Birth of String Theory over on my bookshelf, which tells a lot more about this, is late 1950s nuclear physics, when there was a situation sometimes referred to, well, I wasn't there, but it's referred to in the literature as the particle zoo, which had to do with the fact that in scattering experiments that were probing nuclear, sort of subnuclear physics energies, experimentalists were producing lots of new, strongly interacting particles called hadrons. And it was a puzzle for various reasons. It was upsetting because there wasn't an obvious sense in which some of the particles might be more fundamental than others. There was no sign that they were going to stop discovering new particles. Maybe there was going to be an infinite number of them. It was hard to write down physical theories of type were generally thought to be useful at the time to describe the interactions of these particles. And this was a big problem. And there was a particular take on this problem of the Bootstrap program. I have some little pretend laser pointer that hopefully is showing up, which had a number of names associated to it, but I should mention Jeff Chu because he was at Berkeley, my alma mater, and he's my academic great-grandfather. And the idea of the Bootstrap program was it was a bit of a radical idea. It was a very radical idea, but it was sort of this, it was getting into the 60s. And the idea was to abandon any hope of producing sort of a microscopic account of the interactions of the fundamental particles that people were observing, and instead to try to use general consistency conditions to constrain the possible observables associated to a system of particles. And the observables in question were the so-called S-matrix amplitudes. So the thing people were doing was throwing particles at each other and seeing what came out. And the idea was it might be the case that there are some general mathematical principles that the behavior of these observables had to obey that were so strong that you could imagine just determining the answer, determining what was happening experimentally without having sort of an underlying microscopic account. Oops, I've gone 2 slides. And skipping over a lot of history, in the late 1960s, a gentleman named Gabriele Veneziano wrote down what is his, it's an amplitude, it's a scattering amplitude named after him called the Veneziano amplitude that I've reproduced here, but you shouldn't worry what it looks like at all because I'm not gonna treat it at any level of technical detail. All I wanna say is that as a mathematical function, it has a variety of somewhat miraculous properties that people from this Bootstrap school of reasoning were aiming at the time. So people had sort of refined their thinking on this subject to the point where they had some well-defined mathematical rules that they wanted some functions to obey, and it wasn't obvious that there would be any such functions that obeyed these rules. And Veneziano wrote down something that did obey these rules, and quickly it was generalized by many other people to produce a set of sort of putative Bootstrap amplitudes that were supposed to describe nuclear scattering. I think that the Veneziano amplitude was supposed to describe pion scattering, but it wasn't derived from a theory of pions. It was derived from requiring it to be a nice function that obeyed a bunch of rules. And it wasn't until a couple years later that a few different people realized that there was a way to derive these answers, and the way to derive them was through some sort of a string model, which is, of course, what we're going to be talking about. It turned into string theory. So some model where there was some sort of string-like fundamental object around. Now, history took an inconvenient turn for the early string theorists, which is that also in the late 1960s and early 1970s, a number of theoretical and experimental developments were taking place, sort of giving a different, and we now would say correct, answer to how to explain the previous puzzle of subnuclear physics. So at the Stanford Linear Accelerator, SLAC, the so-called deep inelastic scattering experiments were uncovering evidence for what Feynman called partons, which we now call quarks, which were some sort of smaller particles making up the nuclei of atoms. And then in 1973, David Gross, Frank Wilczek, and David Politzer discovered what's called the asymptotic freedom of non-abelian gauge theories, which really set the stage for the acceptance of quantum chromodynamics as the theory of nuclear physics as we know it. And so this left the string models, or as they were called at the time, dual models, without a home. But no good idea should be wasted. And so a couple years later, Joel Shirk and John Schwartz, and also Yonea separately, recycled the idea of these string models, repurposing them as a possible model of gravitational physics. So the aim was no longer to explain nuclear physics. The aim was to explain quantum gravity. And with this, in this new context, a number of technical advances continued to take place. So there had been some pathologies of the models from the 60s that were overcome during this era. Models were written down that didn't have certain bad things called tachyons and ghosts. A sharper connection between string theory and gravity or general relativity was uncovered in the PhD thesis of Dan Friedan. In 1984, the year that I was born, Michael Green and John Schwartz initiated what has sometimes been called the first superstring revolution, when they explained how to construct really the first, and in fact there ended up being 5 consistent models of interacting strings that were free of all the pathologies that people at the time had sort of been worried about, and which were supposed to be viable as models of nature, where viability is in the eye of the beholder. Jump ahead, 10 years later, the second superstring revolution, as it's grandiosely referred to, was triggered by work by Ed Witten and also Joe Polchinski as sort of 2 main names, but of course there was work by many people. At this time, it was realized that what were previously thought to be a small but greater than 1 number of consistent string theories were actually, in some sense, unified as aspects of a single parent theory, which is called M theory, where nobody knows exactly what M stands for. A few years later, something that has to be mentioned, although I won't have anything to say about it today, was the work of Juan Maldacena, realizing an old idea which went by the name of holography in a technically precise sense within string theory via something called the ADS-CFT correspondence, or ADS-CFT duality. And you should probably have a separate extracurricular lecture on ADS-CFT. Maybe you already have, I'm not sure. And that sort of brought us into what you might call the modern era of string theory. So there have been various interesting advances, and there's been all sorts of interesting work in the last 23 years, but I think that the last really game-changing development of a certain magnitude was this work of Maldacena from 1997. Okay, that was a lightning fast history. And of course, I used various terms which, if viewers haven't studied this at even a pop sci level before, they're not going to really know what I'm talking about in some cases. But hopefully, this will sort of get some of these terms bouncing around in your head, so that then when I say some more over the next hour, it will start to make some sense, some framework. Okay. So that was the historical story at some level of resolution, but I'm not going to follow the chronological development of the subject from this point. I'm just going to start the way that I start in my, my string theory courses, which is to start with the relevant postulate that leads to string theory in the modern view. So string theory is supposed to be a kind of replacement for traditional theories of particle physics. So in particle physics, we talk about particles, incidentally, which when we talk about what we would want to call a fundamental particle is a point-like object. It doesn't have some specific spatial extent. And the postulate of string theory is that there are no point particles. The basic objects we should really be thinking about are, in some sense, little vibrating floppy strings, which could be closed strings, which are some sort of closed loops in space, or they could also be open strings that have endpoints. Both of these can be accommodated. And without saying anything technical, if we want there to be some sense in which this is a viable postulate for how particle physics really works, then we need there to be a sense in which there's a characteristic length scale associated with these strings, which is roughly speaking how big they tend to be when we run into them in the world. And that should be much smaller than any sort of experimental length scales that we can probe with experiments. In the original incarnation of string theory, that characteristic length scale was supposed to be, roughly speaking, the nuclear length scale, which would explain this particle zoo as arising from different sorts of vibrational patterns of the strings. But in the more modern telling, we want the length scale to be much smaller. And then the idea, this sort of, I'm not sure if I'm going to phrase it in a poetic way, but lots of speakers and authors find poetic things to say about this. The idea is that the different sort of characters of internal motion that one of these strings can have will manifest if you're zoomed out and I don't really see the string, but I see something which is roughly point-like, then I'm going to see its internal activity manifesting as what seem like intrinsic characteristics of the observed particle. So if there's some sort of internal kinetic energy to the string, if it's moving around with some energy, then that's going to be incorporated into what I think of as its mass due to Einstein's relation between energy and mass that I reproduced here. So if there's some sort of unobservable kinetic energy, it's going to pass as mass. And similarly, if there's some sort of angular momentum to the motion of the string, then if I don't see its stringy properties, I'm going to observe that as some sort of intrinsic angular momentum, which is what we call spin for elementary particles. So I'm going to get the sort of variety of elementary particles that I see in the world, ideally, aspirationally, from different vibrational patterns of this single underlying sort of string-like object. And it's important that this is a quantum theory. So classically, strings are sort of floppy objects, and whatever kinetic energy or angular momentum a classical little vibrating string would carry would be a continuous parameter. And so we would see particles with continuous ranges of mass and spin, and that's not what we see in nature. And so it's important that we be dealing with quantized strings where these various parameters are going to be discretized. So when we study a quantum string, I'm just going to report results here. This is what you do in your first course on string theory is you work this out. When you study a quantum string and you see that its motion is subjected to the rules of quantum mechanics, then its vibrational patterns are going to be restricted to some discrete set of possibilities. I tried to do some cartooning here to show some ways that strings can vibrate, but of course you should be more quantitative when you work it out. And these discrete vibrational patterns are discrete but infinite. There's going to be an infinite number of ways that these things can vibrate, but they will be organized into a discrete family. And in this view of the world, then those infinitely many vibrational patterns should manifest as an infinite number of increasingly massive particle species in the sort of world of particle physics. Excuse me. So returning to a comment I made before, in the original attempts to use this as a theory of hadrons, this infinite family of particles was considered an experimental virtue because people were seeing lots of increasingly massive particles showing up in nuclear scattering experiments. But in the more modern conception of how this theory might make contact with the world, these higher string modes, so everything but the least energetic of the string excitations are meant to be sort of out of reach of what we can test with modern experiments. So most of the activity, most of the potential activity of these strings is going to be out of sight at real world energies. Okay, that was some sort of, that's sort of the first exercise that you do when you work out what a quantum string is you look at the ways that it can vibrate and figure out how that translates to some sort of spectrum of particles that could show up in the world. The second thing that you do is that you look at the problem of quantizing the behavior of a string from the point of view of Feynman. So Feynman had this beautiful perspective on quantum theory that's known as the sum over histories or sum over paths, or the path integral, which says in the case of point particles, so here I have some cartoon of. Can I ask a question? When I use my little laser pointer feature, it doesn't actually move around smoothly on my screen. It just sort of hops around. Is it showing up smoothly on the viewers' screens, or does it hop around?
No, I think we see the same thing as you.
Okay, so I won't use it. That seems to not be a successful effect. Okay. Maybe I'll draw little arrows when I need to call attention to something. So, so here's the cartoon. If you want to describe a quantum mechanical particle according to Feynman, and you want to describe the rules for how it would propagate from a point called x initial, xi, to a point called x final, x sub f, then you should actually look at all of the possible paths that it takes. And then you do a very fancy thing called a path integral, which is what is indicated in this equation, where you do some sort of an integral, and it's a hard problem to know what these symbols mean, but you're supposed to do some sort of an integral over all of the trajectories that link your initial position to your final position. And those trajectories are called gamma in this expression. You do an integral where each trajectory is weighted by a phase, e to the I over h bar times the action of the trajectory, which if you have met actions in classical mechanics, you know what it is. And if you haven't, then you will soon if you're an Oxford physics student. You compute that quantity, you take its absolute value squared, and that gives you a probability. And Feynman tells you this is how to know the probability of some quantum evolution from an initial configuration to a final configuration. The same goes for strings, only now the pictures are a little bit more laborious to draw. So for a string, you're going to talk about an evolution from some initial configuration of a one-dimensional string in space. This is my capital gamma sub I. And you're going to want to know the probability that it evolves to some future configuration, capital gamma sub F. And in order to assess the probability of that happening, you need to do a path integral over all possible world sheets. So in the previous case, you can think of these trajectories as being the world line of a particle moving through space and time from the past to the future. In this case, we're looking at all possible world sheets, which are the path traced out in space-time by this string, going from the initial configuration to the final configuration. And I drew something to make it clear here that in some sense, I have no excuse to not include, once I'm dealing with this sort of floppy thing, I have no excuse to not include more complicated topologies of the world sheet going from the initial to final configuration. So this one that I drew here that I just drew an arrow towards has some holes in it. So if you know some low dimensional topology, this is a higher genus world sheet going from the initial to the final configuration. And then I'm still supposed to do the path integral, which is now even harder to make sense of, but nevertheless, we can write down the same symbols. And so I want to do an integral over all of these world sheets that interpolate between the initial and final configuration. That's my capital sigmas. And again, I'm weighting these by a phase, which is determined by an action called S, evaluated on the world sheet, which I'm not giving you an expression for here, but there is one. And then I'm going to take the absolute value squared of that, and this is going to give me the probability amplitude for going from the initial to the final configuration. Okay, so I said some words about path integrals. I haven't said anything about how to actually compute these things, and indeed it's a challenge. But I said this because I want to mention an important topic that arises at this point, which is that of anomalies. So it's a deep feature of quantum theory that not every classical theory, and I'm phrasing this in very broad terms, you can make it as specific as you like, not every classical dynamical theory can be consistently quantized. So if you've gotten through your first or second course on non-relativistic quantum mechanics, this may not be a familiar fact. Somehow the theory of non-relativistic single particle or several particle quantum mechanics doesn't see this subtlety so much, but it plays an important role in quantum field theory, which is the relativistic generalization of quantum mechanics. And roughly speaking, you can think of this potential inconsistency in trying to quantize the classical theory as being related to the difficulty of defining these path integrals that I just wrote down symbols for. So being able to write down the symbols doesn't mean that I can actually define the thing. Now, I live in a math department, and in the math department, my colleagues would tell me that you actually can't define these path integrals pretty much ever. It's a hard, outstanding problem in mathematics to define even some of the path integrals that physicists are the most comfortable with. But even at a physicist's reduced level of rigor, it's a challenge to define the path integral, and there are cases where using physics level techniques, you can argue for the impossibility of defining the path integral in a way that is compatible with all of the consistency conditions one would want to impose. And it's when there's an obstruction of this type that we say that some sort of putative theory, some classical theory that you were planning on quantizing suffers from an anomaly. That's a bit of an oversimplification in several ways, but it will serve us for our purposes here. So I'm going to be talking about this anomaly for strings, but it's an important fact that even in theories of even in quantum field theories that are a big part of our everyday life, whether you know it or not. So in the standard model of particle physics, potential anomalies of this type play an important role. And if you are someday going to become a particle physicist who wants to propose extensions to the standard model by including new particles that we haven't yet discovered, it's a very delicate thing to make sure that when you introduce some hypothetical new particles in your hypothetical world, that they don't break the anomaly freeness of your theory. Okay, so I introduced this in order to make the point that this string path integral that I wrote down some symbols for is actually under threat from a number of potential anomalies. So when you actually dig into the nitty-gritty of trying to make sense of this thing at sort of physics level rigor, there are a number of places where things can go wrong. There are actually additional consistency conditions because of the fact that I not only want to define, as it were, these path integrals, but I also want to be able to interpret the results as a sensible theory of physics in space-time. And this leads to some extra conditions. I need to make sure that the thing that I compute when I do this is actually always consistent with a probabilistic interpretation of space-time physics. So probabilities shouldn't be negative. And this means that I don't want certain things called ghosts. And I also don't want to discover any particles in my string spectrum that have negative values for their mass squared. Such a beast is called a tachyon. You may know about tachyons. They're things that naively should travel faster than the speed of light, which is a no-no. So we're going to demand that we don't have any tachyons. So at a very high level, what I'm aiming for is some way of trying to set up this string path integral as I drew the picture for, where the path integral makes sense subject to the rules that quantum field theorists have set up for how to define path integrals, and where I don't have any of these space-time pathologies associated with admissible space-time physics. And these consistency conditions, this is one of the lessons I hope to communicate in this talk, even if we're not getting very technical. These sorts of consistency conditions put enormous pressure on any attempt to make sense out of this theory of strings. You might think that you have a variety of choices when you start setting up this theory, and you're going to start to find out that many things that you thought were choices are actually constrained by self-consistency. So probably the most famous of these constraints arises from an anomaly, which has a name, although you don't need to care about the name. It's called the conformal anomaly. And this has the amazing to some people, I think I would count myself amongst those people, but you can decide how you feel about it. It has the amazing effect of imposing constraints on the dimensionality of space-time. So certainly, as a starting point, I might have thought that one of the things I get to do when I define this sort of theory of strings is I get to choose how many space-time dimensions I'm working in. And probably I'm going to choose 3 space dimensions in one time dimension. And then I'm going to find out that that's inconsistent because of an anomaly. And depending on a little bit of detail, which I have glossed over, but I have some sort of internal structure that I can equip these strings with that I'm not going to elaborate upon. But depending on exactly how I set up the internal structure of these strings, I can get things called strings or superstrings or n equals 2 strings. There's a few other things. But there's some limited set of internal structures that I can equip these things with. And depending on that internal structure, I end up with a sharp constraint on the dimensionality of spacetime. And this is probably a fact that anyone who has watched a NOVA special on PBS or read a book by Brian Greene is aware of, but I'll repeat it here. The basic version of string theory, which is what's called bosonic string theory, you find out that space-time needs to be 26 dimensional, 25 space dimensions in one time. In the slightly fancier superstring theories, you find out that space has to be 10 dimensional, 9 space dimensions in one time. In one of these more structured systems called n equals 2 strings, which don't get much attention in the popular tellings of these stories, you find out that there are 4 dimensions, 2 of which are space and 2 of which are time. So let's not worry about that. I don't want a theory with more than one time direction, I don't think. But already this is one of the remarkable things about these theories is that they even have an opinion about how many space-time dimensions there should be, just by virtue of the fact that the elementary objects are strings rather than particles. You can make perfect sense of a theory of particles in all sorts of number of dimensions, but strings care. Right, so this is a surprise, an impressive surprise to many people. I think that you should be surprised, although you might have already known it, in which case you are not surprised. And in some superficial, but it turns out not so superficial way, it suggests that there should be some deep dialogue between the sort of the behavior of strings and the structure of space-time itself. We really can't divorce the question of how these strings behave from the question of where they're doing it. They care where they live. So this is indeed the case, and it turns out to be the case in sort of increasing levels of sophistication. So I claimed that there was a particular anomaly, so a particular way for the path integral to break down led to this requirement that space-time have correct number of dimensions. There's a more refined analysis of this same anomaly, of this same potential flaw in the definition of the path integral, which actually shows that in order for these strings to propagate consistently, so in order for the path integral to be well behaved, that it's required that the space-time in which they're propagating obey Einstein's equations of motion, Einstein's equations of general relativity. So Einstein produced these beautiful equations for how space-time should be shaped, which is his explanation for the phenomenon of gravity. And string theory gives you back those same equations as a consistency condition. It's slightly more subtle than that. It gives you back those equations as a consistency condition at sufficiently long distances. Again, there's this hidden length scale that I mentioned before, the string length, which characterizes, roughly speaking, the size of the strings. And the prediction is that Einstein's equations have to hold at distances which are large compared to the string scale, with some sort of specific corrections that are, again, controlled by self-consistency of the quantum string at shorter distances. A related but not obviously equivalent fact, although then if you pick up a string theory textbook and read it through, you'll realize that they are equivalent. But originally a different observation was that in these string theories that I mentioned that obey these rules in terms of the space-time dimensionality and the absence of these anomalies, one of the string modes, so one of the vibrational patterns of the string, can always be identified as the so-called graviton. So this is the quantum particle that carries the force of gravity. So this is a confirmation that string theory is thrusting gravity upon you, is that you find gravitons in the spectrum of particles, even if you might have had some aspiration to build a stringy theory of particle physics that didn't include gravity. You get the graviton for free, or maybe even if you didn't want it. So in this sense, you're seeing that, or I'm reporting, but you see when you really delve into it, that the dynamics of space-time itself, which is the subject of general relativity, and at the quantum level is the subject of sort of the quantum behavior of gravitons, is all subsumed into the rules of string dynamics. And these observations tell you that to the extent that you can force these string theories to behave in a self-consistent fashion, you are producing theories of quantum gravity, because these are quantum mechanical theories of many particles, because the string has infinitely many excitations, but amongst them is the graviton, which is going to carry the gravitational force, and you get it inside of a quantum mechanical framework. This is, excuse me. This is a famously difficult problem to fit gravity, general relativity, into a quantum mechanical framework. And I would argue that the fact that you get some sort of quantum gravity theory out of strings, regardless of any additional questions that you might run into in the second half of this talk, is probably one of the most robust motivations for people having studied string theory quite a bit, but also for us continuing to study it quite a bit. There are not so many theories of quantum gravity around. Depending on who you ask, the number outside of string theory might be 0, but some people might say it's more like 1 or 2, and people would, it's a contentious issue. People will argue about the status of different candidates, but certainly string theory is one of the few candidates, and it's probably the one that's received the most attention. Okay, so I want to illustrate with a slide with some cartoons on it. I want to illustrate sort of a bit of the message that you start getting as you try to define your string theory and force it to be self-consistent. So the starting point is this thing that I have sort of kept the rug over, which is this issue of what sort of internal structure you equip your string with. And I'm going to continue to keep the rug over that and ask that you take it on faith that there's some sorts of choices that I can make that are well defined. But there's not so many. And then, so going back to the starting point before any of the arguments I already made, first thing you might think is, well, surely I can choose what sort of space-time dimension I'm working in. But no, we saw that actually that's going to be fixed by this anomaly condition, by self-consistency. I get whatever I get in terms of space-time dimensionality. And then I might say, okay, well, you've told me to work in, say, 10 dimensions, but surely I can choose to study strings propagating on some particular 10-dimensional space. Depending on how much differential geometry you know, you might be able to define various interesting 10-dimensional spaces where a string could live. But no, it turns out that you don't get to choose whatever you want. you're constrained to study strings living in spaces that are obeying Einstein's equations of gravity. And in fact, you don't really get to think about it as you choosing the background, because gravity itself is necessarily dynamical in your theory, because string theory contains gravity as one of your propagating degrees of freedom. And so, in fact, the background is not something that you get to fix. It's a dynamical variable in your theory. And then you might say, okay, well, now let me, if I was a point particle theorist, if that were a phrase that people used to describe themselves, if I was a point particle theorist, I would choose the particles and then I would choose their interactions. And I could maybe tune their interactions in various ways depending on my for the day. But actually, once you start drawing pictures of string interactions, you see that you actually don't have anything that you can choose by hand, because interacting strings are just strings coming together and merging and then splitting, as I've tried to draw in these little cartoons. And there isn't really a particular interaction point where the interaction takes place. All I have is some sort of blob of string with various legs going off in different directions. And so it turns out that the only thing that you can really control, I can't choose sort of details of the interactions. I can just choose an overall coupling strength. So it looks like you can make a choice that says that if I have strings that interact once, I pick up a power of some coupling constant that's called G sub s for the string coupling. And I have it so that the string sort of merges and splits twice, then I get more powers of that coupling. So at least you have that coupling, right? At least you can either study strongly coupled strings or weakly coupled strings or intermediately coupled strings. But no, you don't really have that choice either, because it turns out that the string coupling is dynamical too, just the way that the space-time geometry was. There's a string vibrational pattern, there's a string mode called the dilaton that controls exactly this string coupling. And so fluctuations in that string mode correspond to changes in the string coupling. And this is something which is going to be determined dynamically instead of by you. And then coming back to our original picture where we had some potential choice of the internal structure, if we also demand that the theory not have tachyons, so not have any sort of unphysical particles with negative mass, and that there be a reasonable space-time interpretation, I don't want a theory where there's two time directions in space-time, then you start crossing out options there, and you're left with a very limited collection of things. So this is where things were in the early 1990s. People had observed that if you really start imposing all of the consistency conditions that you would want, both for sort of just well-definedness at the level of the quantum theory, and also some of these space-time conditions, you're left with 5 string theories, 5 superstring theories, which I've drawn as 5 dots here. They have various names that mean things, but which won't mean things to us right now. And this was already pretty good, I hope you'll agree. You started out saying that instead of particles, I'm going to study strings. If you study particles, you have a veritable infinity of choices of how you describe, of what, you could have an electron, you could have a muon, you could have quarks, you could not have quarks, you could have 5 electrons. There's all sorts of choices you get to make. You get to choose how they interact. Here, we end up with 5 options. And then in the second superstring revolution, the reason it was a revolution was that Instead, these are the sort of limit points of some kind of an, it's not really an octopus because there are 6 legs instead of 8, so a sextopus. These are limits of a single underlying theory, which is this thing called M theory, which remains to this day quite mysterious. One of the interesting things about this development, well, there were many interesting things about it, but one of the most surprising things about this development was that upon the sort of inclusion of all of these superstring constructions into this overarching M theory, a new sort of extreme limit arose, which I've put at the top of the M theory diagram, which was actually an 11-dimensional theory. So the superstring theories were all 10-dimensional. And then once they are included into M theory, there's a new limiting configuration, which looks like an 11-dimensional theory, what's called 11-dimensional supergravity, which is a theory that doesn't actually have strings in it at all. It's also the least well-defined of these 6 limit points that I've drawn on the diagram. So the superstrings are sort of better starting points for any sort of systematic investigation than this 11-dimensional thing, but nevertheless, there is another limiting configuration. So we know, as an aside, I don't think I have this written on any slides. Certainly the way that I've presented it, this M theory object is a sort of mystical character that appears. A certain amount of mysticism remains in the state of the art. People have learned to say more things that we're confident in about what's going on in this intermediate region that's supposed to interpolate between the different string theories. But one of the outstanding questions, which is really a big problem, is that we don't have a sort of underlying definition of M theory, this thing that lives in the middle, which is on par with our definitions of the theories that live at these, well, not the top one, at these cusp points. So in some sense, when we're studying superstring theory, we're studying some sort of expansion. You can imagine doing some sort of perturbative expansion around these limiting points in this space of theories. And the problem of being able to continue into the interior is a problem of being able to go beyond something like a Taylor series for a function and get some sort of analytic control over the function at generic values of the arguments, which is something which, depending on the function, you might be able to do. And in this case, it's much more complicated than a function. Okay, but the slogan, which I think that you should take seriously, is that all of these theories are now part of a unique theory. Whatever M theory is, and it is a problem to define it in concrete terms, it is a single dynamical theory that realizes the different superstring theories as limiting configurations. So it's not a space of theories, it's a single theory with a space of configurations or behaviors. If you're using the language of quantum field theory, you would say it's the space of vacua of the theory. And so the point is that in principle, you can get around this diagram dynamically. It's not something where God has to tell you which point you're at. The universe, if set up appropriately, can move from one point to another, the stringy universe. Okay, I don't want to meditate too much more on M theory. It is a mysterious subject. I want to come back to something a little bit more concrete, which is what one should do with these 10 dimensions. So this is always a funny part of my string theory course when I teach it. There's this big lead up to when you calculate the dimensionality of space-time, which seems like an exciting thing to be able to calculate. And then the answer is 10. And isn't that a disaster and a failure? Well, it depends a little bit on perspective, but it's not immediately a terrible failure. Because 10 has the virtue of being bigger than 4 and not smaller than 4. And if you err in the right direction, you can fix your errors. The idea of extra space-time dimensions are actually an ancient idea, not ancient, an old idea, ancient compared to string theory. They were proposed as a possible situation in the world almost immediately after Einstein published his theory of general relativity. So general relativity, the finalized version was presented in 1915, and 4 years later, oh no, I've forgotten his first name. Anyway, Kaluza proposed, and then it was later improved upon by Oscar Klein in 1926, proposed that perhaps we could describe some aspects of the actual world we live in by supposing that the real universe has more than 4 dimensions, but some of them are small. So we shouldn't observe some dimensions because in an appropriate sense, they are too small for us to see. So here's the cartoon. You start out with a space-time. So you have a theory that you think of as being a theory of here I've presented as 4 plus n dimensional space-time. So 3 plus n spatial directions plus a time direction. And then you perform a procedure. This isn't like a thing that you're talking about doing in nature in the world. It's a theoretical procedure, which people use the word compactify to describe the situation where instead of considering just some sort of 3 plus n dimensional Euclidean space as your model of space along with time, you take 3-dimensional Euclidean space as we know and love it, and then you additionally have some sort of n-dimensional space that I've named x sub n here, which is curled up. And depending on your geometric skills, you have more or fewer techniques available to you to describe those spaces quantitatively. Is somebody asking a question? Or is somebody just have a microphone turned on unintentionally?
Yeah, sorry, I should be fine now.
Okay. Right, so in this picture, the idea is that this space, which I've intentionally drawn as a space of finite extent, this x sub n, its size is supposed to be much, much smaller than any sort of macroscopic or even microscopic, maybe, scales that we encounter in our world in order for this to be compatible with the way that we encounter the world. And in a quantum mechanical world where particles sort of smear themselves out because they have wave functions instead of definite positions, the picture is that we're actually going to be sort of spread out in these extra dimensions, and so we're not going to be able to notice any sort of local dynamics in the extra directions. We're not going to be able to localize any structure in them. without having enough energy, without having more energy than we bring to bear in ordinary daily circumstances. In the original theory of Kaluza and Klein, which is abbreviated KK, they were just considering the case where n, in my picture here, was equal to 1. So you started out with a 5-dimensional space, but then you let one of your spatial directions be a circle. And it's an interesting observation, which is the one that they had back then, that if you put general relativity on a 5-dimensional space that looks like 4 dimensions times the circle, then at low energies, the 4-dimensional theory is going to look like a theory of gravity plus a theory of electromagnetism. So this was the insight that they had, was to try to get the electromagnetic force that we have in the real world as an effect of an extra dimension. Now, in string theory, we're going to be interested in compactifying on compact 6-dimensional manifolds, so 6-dimensional spaces that are sufficiently nice. And this is a much more complicated endeavor than looking at circles. And you need to call your geometer friends to tell you about their favorite six manifolds. I stole a picture from Wikipedia. There are strong constraints on the sorts of spaces that you can compactify on, for the same reason that we were running into constraints already in 10 dimensions. And a popular class of spaces are so-called Calabi-Yau manifolds, named after 2 mathematicians. And the idea is then that the structural properties of this higher dimensional space, which is hidden away from us as low energy observers, will translate via some dictionary into some properties of the low energy 4-dimensional physics that we will see. So there should be some dictionary mediated via string theory that goes from the information of these extra dimensions to the information of the low energy physics that you could observe. And that's implementing that dictionary is a hard problem, too hard to solve in many cases, although in large classes of cases it is understood. The generic cases is probably too hard. But already at a heuristic level, this is an area where people declared some success early on. And this is because when you take these 10-dimensional superstring theories that are the consistent ones, and you look at what you're going to get in 4 dimensions if you compactify on the allowed types of spaces, then you get certain ingredients which are the right sorts of ingredients for particle physics as it's been successful in 4 dimensions. So for people who've learned a little bit about the standard model of particle physics, you naturally encounter non-abelian gauge symmetries, non-abelian gauge theories, as well as chiral fermions. So fermions and chiral representations of those non-abelian gauge theories. If you don't know what those words mean, those are exactly the ingredients that are used to describe the standard model of particle physics, which is enormously successful in broad terms. So I haven't told you that you get the actual standard model. I've told you get the sort of right mathematical objects, which are the sorts of ones that appear in the standard model. You also naturally encounter certain popular ingredients which have, at least as recently as not that long ago, been popular ingredients in speculative extensions of the standard model. So supersymmetry, the super in superstring theory is related to supersymmetry, and you naturally get supersymmetric 4-dimensional physics out of this, as well as what are known as grand unified theories. And these are both sorts of theories that people had spent a lot of time proposing and ironing out the details of as proposed extensions of the standard model that we were supposed to uncover details of at the Large Hadron Collider within the last decade. One of the major developments of the last decade of experimental particle physics is that the Large Hadron Collider did not uncover anything other than the standard model so far. And so many popular speculative extensions that people suspected might be correct have been ruled out. And so it's no longer clear how excited one should be about the fact that these things naturally fit into the world of string compactification. And I should say, finding an actual string compactification, so finding an actual configuration of one of these 5 superstring theories that at low energies in 4 dimensions looks really just like the standard model as we see it, as we know and love it, remains an open problem. So there isn't a construction that somebody can write down and hand to you and say, well, this fits all the data that we have so far. Okay. So this brings us, I guess this has been sort of a spotty romp through the history of the subject, but it brings us up to the relatively recent past, and the observation that despite the sort of moral uniqueness of string theory, so I claimed that in some sense there were 5 string theories and 1 M theory that realizes all of those string theories. In a practical sense, there's an enormous non-uniqueness of string theory, which comes from when you actually look at the different possible, what people would call vacua or vacuum configurations. So the ways that a string theoretic universe can settle down at 0 energy and sort of behave. So we could have one of these Calabi-Yau manifolds with some of the dimensions wrapped up. We could have more dimensions wrapped up. And here's a picture that I stole from the Kavli Institute for Theoretical Physics website. Here's a landscape. And along the top, you see what are supposed to be representations of lots of different Calabi-Yau manifolds. And all of these are viable ways for a stringy universe to arrange itself. And this is a problem if your aspiration was to use the string postulate, the string hypothesis, in order to end up with a prediction for exactly what low energy physics we see in the world. Because despite this moral uniqueness, the possible low energy physics is unfathomably non-unique, or at least this appears to be the case. I should say there's a question mark in this line that appeared at the bottom, because it does remain a bit a subject of some debate how what level of confidence there is in some of the constructions involved in getting these numbers. But it's been argued that there could be upward of 10 to the 272,000 different ways of a 10-dimensional stringy universe sort of arranging itself down to 4 dimensions. That is an impossible number. And that at that point, you really have to decide how you're going to spend your time if you were studying these things. And at this point, people start having sometimes not so civil conversations about the falsifiability of such a theory, which is compatible with so many different versions of low energy physics. What sort of experiment could you ever do to confirm or deny the correctness of string theory as the theory of our universe? And indeed, this is a contentious issue. People write books about it. They sell a lot of the books. I included covers of some books by people arguing that this is a bad situation for string theory and for physics. There are other books that I didn't include by people arguing that it's not so bad. But it's obviously an issue. People approach this situation with different strategies. You could imagine trying to do some sort of statistical analysis of this so-called landscape of different low energy configurations of string theory. This could maybe be coupled with some sort of dynamical arguments about the way that the universe sort of populates these different vacua. The word multiverse starts to appear in these conversations, and then people get very angry. You could also hope that we get lucky and that somebody does an experiment which uncovers some sort of characteristically stringy physics. Maybe the energy scales associated with string excitations, these higher string modes, are not so out of experimental reach, and somebody will build a new collider in Switzerland, and they'll be able to detect something which is really identifiable in a stringy sense. Something which has been getting, I would say, an increased amount of attention in recent years has been the question of whether, in some sense, you could show that strings are an inevitability in a theory of quantum gravity. This is an upgrade of what used to be called the only game in town argument, which was the argument where you said nobody else has any very good ideas about quantum gravity, and so we should believe that string theory is more likely to be correct for this reason. Oops, can I get it? The research community could also be missing something at the moment, or the story could be incomplete. There may be some sort of inconsistency with large parts of the landscape. I'm certainly not trying to convince any of you of the relative virtues of any of these points of views. I think that there's lots of different ways to come down on this subject. I would roughly identify myself with this final line, which is that even though this is a subject that's been around for a long time, it's clearly still a work in progress, and there's enough there are enough questions structurally about the way that string theory works that we're not lacking things to study to try to build a more robust picture of the subject. And it's not a game that you probably want to get into if your hope is to predict the result of an experiment that somebody is going to do in the next 50 years. You never know, but I wouldn't get into it with that intention. Incidentally, I now work in a math department, so that's the sort of thing that can happen. And I would underline this item that quantum gravity is a difficult subject, and so even if you are a maximally pessimistic person, and I wouldn't encourage you to be one, but you can be one. Even if you're a maximally pessimistic person about the prospects for sort of connecting string theory as a theory of particle physics in the real world with experiment, you should not ignore a theory that appears to be a quantized theory of gravity, because at the very least you will study it as a toy model, and it will be one of the only toy models you have access to. And this has certainly been the approach of a large part of the research community, especially in connection with this ADS CFT correspondence that I mentioned in the introduction, but haven't said anything else about. That's a point of sort of deep there's a lot of deep structure of quantum gravity which is accessible through that correspondence, which is strongly informed by having a microscopic model in terms of strings. Okay, so that was the overview, leaving off on a somewhat ambiguous note from a sort of phenomenological point of view. Now I want to spend a little bit more time talking less about string theory as a potential replacement for theories of particle physics, and more talking about what some surprises that come from thinking about the interplay between ideas in string theory and ideas of space-time geometry, the idea that a theory of gravity involves some sort of dynamics of the geometry of space-time. So I would start with a very vague question, which is, how should one think about space or space-time in a stringy universe, whether that's our universe or not? Well, here's space, I guess. Well, what is a space? If you're a mathematician, and even if you're not a mathematician, then at some intuitive level, I think that you think this. Space is some sort of collection of points which are equipped with additional structures. So there's some notion of sort of proximity, which points are close to other points, and that is that's what's called a topology on a space. And you might want a little bit more than a notion of closeness. You might want a quantitative measure of distance, in which case you're talking about a metric space. And indeed, in general relativity, we formulate space-time as a metric space, a pseudo-Riemannian manifold, if you're being precise. And in a sense, it's sort of obvious that this collection of points that comprise a space in the intuitive sense are precisely the possible positions of a point particle. So point particles as the idealization of objects in space are quite natural. They are the things that occupy sort of the smallest spatial entity. And so I would claim that our intuitions for how to think about space, both physically and mathematically, are very much sort of point particle intuitions. You might not think about it that way, but secretly I claim they are. So if we're studying a theory where the fundamental objects are strings, it makes sense to ask how a string sees space. And it's not just how a string sees space when there are also point particles around that can also see the same space. We're talking about a situation where there are only strings. So in some sense, to the extent that our intuition for the structure of space is built on the configurations of points, we might have to do a more, we might have some sort of radical revision to do once the basic objects are different. So here's a little cartoon. So to a first approximation, there's a picture of a string probing what looks like probably the surface of a globe, so some sort of a two-sphere. And in a limit of what a string theorist would call perturbative string propagation, the way that this little vibrating string sees the space it's on is not so much different from the way that a point particle would see the same space. It might be blurred out a little bit, because if I have a string that's sort of oscillating a little bit, then as it moves around, it sort of detects little neighborhoods all at once. But it's sort of a fuzzy version of the original take on how a particle would see the space. But of course, a string can do a more dramatic thing. If I want to go from the initial string position that I drew up here to the final string position that I drew down here, another way for a string to do that is to sort of expand and go around the sphere in some sort of trajectory that sees more of the global structure of the space in which it lives. And this is an operation that really doesn't have an analogy in the behavior of a particle. This isn't a small correction to the way that a particle propagates through a space. This is a large correction. And roughly speaking, this sort of a process is something that a string theorist would call a string instanton, but you shouldn't worry too much about the terms. And so at a qualitative level, I want to claim that these sorts of big differences in the ways that a string can see an interesting geometric or topological space could lead to some big surprises in the way that we sort of conceptualize the space. So here's an example. So this is actually going back to the simplest example of a compactification, which was this one of Kaluza and Klein from back in the start of the 20th century, where we imagine a world where there's a single compact periodic direction. So one direction looks like a circle. And for the purposes of illustration, I've drawn another direction. So in this case, I have one sort of infinite direction and one circular direction. So it looks like a cylinder, but you could have more non-compact directions as well. And if we think about it, the way that a string lives in this cylindrical world, there are two subtleties compared to the case of a string that's just vibrating around in flat space, in sort of infinite Euclidean space. Well, the first is a feature which is already present in Kaluza and Klein's theory of ordinary, sort of ordinary particle physics on a circle. This is a feature, this is something that arises from quantum mechanics, so some of you will sort of have an intuition for this, but if you don't, you'll take my word for it, that in a quantum mechanical world, if you have a compact direction, then the momentum of an object in that direction gets discretized, gets quantized in units of 1 over the radius. This is, I'm working with some convenient units where h bar is equal to 1 in this setting, called natural units. But a particle moving on a circle, a quantum particle or a quantum string moving on a circle can carry momentum sort of in the direction around the circle, but it will be discretized. But a truly stringy effect is that also strings can wrap around a circle. So I can draw a string, I can have a string that sort of starts here and it goes around the circle once and it closes back on itself. And it's like really winding around the circle, and it can't be continuously deformed to something that isn't winding around the circle. And if you're interested in low energy physics, meaning physics to a person who can't resolve the internal structure of this circle, then they're going to see particles corresponding to strings that wind some number of times around the circle, W, and that have n units of momentum around that same circle. given by the equation I've written here. So the mass squared, and here I'm also working in units where c is equal to 1. This is, if you haven't learned about natural units, it will make your life great once you learn about them. C and h bar are equal to 1. So the mass squared of these particles, as observed by the person who cannot resolve the structure of the circle, will be whatever the mass squared was of the sort of intrinsic object, along with contributions from the kinetic energy corresponding to the momentum around the circle. That's this n squared over r squared. Along with some extra energy corresponding to the fact that my string is stretched out around the circle. So the string has some tension, which I can work in units where it happens to be 1 over 2 pi, but that's not that important. And so you see that a string that's stretched is going to have an energy which translates to its mass, which goes like the square. Its mass squared is going to go like the square of the number of times it's wound. So the first two terms here are present in Kaluza-Klein theory, if you just want to talk about a particle moving on a circle. And the last term is a stringy term. And the interesting thing about this extra term is that it makes this formula symmetric under this exchange operation. So if you replace momentum around the circle with winding around the circle and vice versa, and if you also replace the radius of the circle with 1 over the radius of the circle, then you end up with the same equation. Now, that's a symmetry of an equation, but an amazing fact is that this is more than a symmetry of an equation. It's actually a symmetry of string theory in its entirety. And we refer to these as string dualities. So to a quantized string, a circle of radius r is literally indistinguishable from a circle of radius 1 over r. Small and big are indistinguishable from one another. So that's an explosive fact, so it gets an explosive graphic. This equivalence is known as T-duality for historic reasons. The name doesn't really do it justice. And there's really it's really a surprising fact at any sort of intuitive level. You have to see it. I mean, you almost shouldn't believe me for saying it. You should go learn string theory so you can derive it, because it's an amazing fact that you have to see how it really works to believe. So the strings that are winding around a circle of radius r behave exactly like strings that are not winding, but which have momentum moving around a circle of radius 1 over r, and vice versa. Now, just as a sort of reality check or a sort of gut check, I've been working in units where all sorts of things are 1, and in particular, I'm working in units where the so-called string length is roughly equal to 1. So what this is saying is that if you try to study string theory where your strings move on a circle which is smaller than the characteristic length scale of those strings themselves, then you're going to have a better description in terms of a dual circle which is bigger than that characteristic length scale. But I really want to emphasize that this is an exact equivalence, and neither of these descriptions is more fundamental or correct than the other. It's not that you've really got a space-time which has a radius radius r, and then you can sort of get it to look similar by studying a space-time with radius 1 over r. In a universe where the fundamental objects are strings, nothing can tell the difference. because the fundamental objects are the things that can't tell the difference. And this is just the tip of the iceberg in some subject that might get called stringy geometry or string geometry, which is this question of sort of how do quantum strings see spaces. So you see now I've slickly made a transition from this sort of fraught issue of whether I should use string theory to describe fundamental physics in our world, and then people are going to yell about falsifiability, to this very beautiful question of mathematics that string theory has forced me to think about. Sort of how does geometry work even when I don't have point particles, but I have strings? And this is a very pure question that nobody gets to yell at me about this question. So I'm almost done. I've probably gone a little bit longer than I intended. I want to draw one picture which illustrates sort of the on steroids version of this phenomenon I just described. And you're gonna, if you're not much of a geometer, you're gonna have to take it on faith from me that these pictures I draw sort of represent real things. So the souped up version of what I just described is a situation where you have a 2n dimensional space. So earlier we liked 6-dimensional spaces to get from 10 to 4. So 2n might be 6 with n equals 3, although that's not what I'm going to be able to draw. We have a 2n dimensional space, which is what's called a fibration by n tori over an n dimensional base. So here's something which is supposed to be a picture of that, where n is equal to 2. So the base is some n-dimensional space, which in this case is a 2-sphere, because that's my favorite 2-dimensional space. And then saying that I have a fibration by n tori means that each point on this base has sort of a 2 torus living over it, but the precise shape of that 2 torus can sort of vary smoothly as I move around in the space. So here I've drawn sort of some select points and a torus living over each of those points, and you can see that I've drawn slightly different shaped tori corresponding to where I am. Even exotic things can happen where the torus sort of degenerates, which is what happens in this purple picture. But this is a nice structure that you can ask a space to have, and in fact a surprising number of Calabi-Yau manifolds have this structure. And now you notice that a torus is like several circles put next to each other. And we just had a deep insight into the way that strings interact with circles. Sorry, go ahead. So there's a fancy version of the T-duality operation I described before, which is called mirror symmetry. And the version I'm describing now is actually called SYZ mirror symmetry, named after Andy Strominger, Xingteng Yao, and Eric Zeslow, who wrote the paper describing it. And this is a duality where I take this original space that I had my sort of cartoon picture of, and I imagine doing T-duality on all of the fibers. So all of these tori that are fibered over the base. And then I'm going to get a different space, which has a tilde on top of it, which is the space where sort of all of these circles are replaced with their dual circles. And it might seem like you're really only going to sort of change sort of the size of some stuff when you do it, because with the circle, with the circle on its own, I was just changing the radius from one value to another. It was still a circle. And this is maybe not something that's easy to have intuition for, but once you use the same operation in this souped up setup, you can end up with spaces that really look totally dissimilar from one another. And of course, to observe their dissimilarity, you need some tools of higher dimensional geometry, because these are some higher dimensional spaces. But I hope you'll believe me. And then in this much more elaborate setting, we still have the claim that strings probing one of these spaces are exactly equivalent to strings probing the other space. They cannot distinguish between them. So in this case, you have much different looking spaces from one another. They differ in more than just the size of some circle. They differ at the level of their basic topological shape, which as far as strings are concerned are equivalent. Now this is a non-trivial fact mathematically, and a fun game to play is to try to turn this into sharp mathematical statements. So once you know that strings looking at these two different spaces are supposed to see the same thing, you can ask what that means in terms of traditional notions of geometry. And this will be my final comment. And I'm mentioning this, I'm mentioning this not only because it's a beautiful story, but because two of the four people who originated this observation are Philip Candelas and Xenia de la Osa, who are two of my colleagues here in the Mathematical Institute. So once you have these mirror manifolds, as they're called, these pairs of spaces that are related by this operation, you can ask physics questions associated to one, figure out what sort of computation you're supposed to do to get the answer, ask the same question on the other, figure out what sort of computation you're supposed to do on the other to find the answer, and then you're required to get the same answer by physical consistency, but then what does that mean for you mathematically? And it can mean very surprising things. So it turns out that there's a class of string amplitudes, so a class of sort of string calculations that you can do, where on the first of your spaces, only perturbative string propagation is relevant. So I had this picture before where I looked at the way that a string explored a space, and perturbative string propagation meant that I basically see the space the same way that I did with point particles. So in other words, if I only perturbative string propagation is relevant, I can basically do the calculation as if my strings were point particles. But on the other side, doing the same calculation requires taking into account these more dramatic deviations from particle motion that were these string instantons, where the string sort of moves in big stringy ways. And it turns out that the math problem that you're led to lives in a world of something called enumerative geometry. So this is a field of mathematics where you look at a space and you try to count various sort of structures within that space. In this case, you're counting sort of the string instantons, or the places, or the sort of ways that the string can do these big moves that I had the cartoon of before. And the equivalence of the two tells you that you can answer some difficult enumerative geometry problem in terms of classical geometry of the mirror manifold. And this is a bit niche, but it's a point of a claim to fame for string theorists, because this sort of mathematical side of this question really came to the fore. I didn't prepare a slide on this, so I'm going to have to try to say it correctly in real time. There was a particular enumerative geometry problem that arises in this way, where mathematicians had done a careful calculation and they got a different answer than what my colleagues got using this string theoretic magic. And there was a big conference at MSRI in Berkeley where they got together to figure out who was right and who was wrong, and the string theorists won. And so this is the great story of the triumph of the string theorists over the mathematicians. But really, it was just a little thing that sort of made the point that these tools were viable. And now there's a really rich dialogue in the sort of string theory mathematics community, where more and more of the tools that are coming out of quantum physics and string theory are being incorporated into honest to God rigorous mathematics, and vice versa. Okay, so let me just put up what was going to be my final list of take-home messages. I think that I've taken more than enough of your time for me monologuing. I gather from the chat that there might be some questions, so maybe people can read this last slide that I wrote down if they're interested, and I'll be happy to take questions.
Thank you so much. Yeah, I guess it's hard to put such a big topic under a time constraint. Yeah, thank you so much. That was a great talk. We had so many more participants than we thought we would. So, which is why, at the beginning, we went a little bit over the participant limit. So some people might have missed the beginning. But if you're here and you missed the beginning because you couldn't get in, you will put this talk on YouTube. So don't worry about that. Okay, so let's start with questions. Oh yeah, so the person who just reposted their question, would you like to unmute yourself and ask it in person? Otherwise, I'll read it out. All right, let me read it out. Could we reflect? I can't. I'm sorry. Okay, no worries. Could we reflect a 10-dimensional string on an n-dimensional spacetime where n is less than 5, 1 dimension of time, like we reflect a 4D object on a 3D space? And if we can, what problems might occur? So I guess this is a question about like wrapping up dimensions. I might have to reread this. It's in the chat.
Yeah, I see it in the chat. I'm not sure that I'm parsing it correctly. I'm not sure what the sense in which you're using the word reflect.
They project is what they mean. But could you elaborate? Yeah.
You mean project? Can you elaborate a little bit more? Because I haven't, yeah, I'm not sure. So how do we project a 4D object on a 3D space? What is your operation you're referring to?
How about we give this person a bit more time to maybe write a bit about it, because it sounds like we don't have a microphone while we take other questions, because it is quite late and I want to make sure that we can get to cover. We'll get back to that. So if anyone else has questions, feel free to put them in the chat. You should be able to unmute yourself as well. All right, while people are typing, I guess I can start with questions. So when you say, so I never did string theory theoretically during my undergrad. I'm kind of always, when I hear these talks, struggling to understand how you would write it down mathematically. Like a particle has a point, like a location. How would you write down where, like, what a string is, where it is? What are the like fundamental like variables that describe it?
Let me so I'll answer, but let me, I think the traditional answer, and I think probably the useful one, is to work sort of via analogy originally with how you would talk about just a trajectory. So if I have an ordinary particle moving through space-time, what we really, so if I have a particle world line, is that showing up? Maybe I can make it a little bit. If I have a particle world line, then I can formalize that as a map. Let me call it gamma, because that was what it was in my slides. From R into whatever my space-time is, which is already, in principle, that's a well-defined object. But if I want to really sort of be concrete and do computations, then I'm going to need to introduce some coordinates on my space-time. So if I want to introduce some coordinates, I might call them x0, x1, up to xd minus 1 under the convention where x0 is sort of the time direction. So this space-time might just be sort of Lorentzian space, in which case these are my usual affine coordinates on Lorentzian space. But if it's some more complicated space, I'm going to have to work in local coordinates in sort of the world of differential geometry. And then this map is just a bunch of functions of a parameter. So having this map means that I'm going to have x0 of s, x1 of s, so on, xd minus 1 of s, where s is in R. And I might have a convention that for a particular propagation, I'm parametrizing it between s is equal to 0 and s is equal to 1 or something. So this is the case for a particle. And then for a world sheet, world sheet, I'm going to have a map, what did I call it? I called it capital gamma. And this is going to be from some two-dimensional space into space-time, where now I'm going to have an opinion about what sort of a string trajectory I'm looking at. So if I just want to talk about something that looks like some wobbly string going from one sort of string configuration to another, this thing is topologically a cylinder. So I can think of this sigma as being a cylinder. Cylinder with coordinates, let's call them sigma and tau, where sigma is identified with sigma plus 2 pi. So sigma is a periodic coordinate which sort of measures around, and tau is like the time coordinate that measures along. And now I'm going to have, again, the space-time coordinates as x0 now of sigma and tau, x1 of sigma and tau, xd minus 1 of sigma and tau. And these are going to be my dynamical variables that tell me about the embedding of my string world sheet into the space-time. And this is a key point that it's sort of illuminated when you write it this way, is that this, in this sort of point particle version, this was a bit overdone. If you've done a little bit of quantum mechanics, this isn't the way that you usually describe like a particle's motion in quantum mechanics. What you would do in quantum mechanics is you would say that like, let x0 of s be equal to s. Let me work with some parameterization where I'm parameterizing by time because x0 is the time coordinate. And then I'm going to get my other coordinates as functions of time. And that's the sort of description that you have in ordinary quantum mechanics. But you can turn it back, you can revert to this description if you want. But now we see that our fundamental dynamical variables in the string, in sort of the quantum string theory, are fields that are functions not of just a time parameter, but a space parameter, which is on the world sheet. And so in this sense, the string path integral that I was talking about becomes a kind of two-dimensional quantum field theory path integral. Because these things are like scalar fields on the world sheet. And so the reason that you end up with all of this sort of strong anomaly business is that it's sort of generic that once you start studying quantum field theory, you start running into these anomalies and have these strong constraints. So indeed, when you actually try to turn this into a calculation, the calculation you find yourself doing is a calculation in two-dimensional quantum field theory.
Well, that was illuminating. Makes me want to check out the problem math. Okay, thank you. We have another question in the chat, but first we have a clarification from our previous question answer. So I think what they were trying to say with projecting onto lower dimensions was less can we get rid of extra dimensions in the maths and make it easier, but more can we project down to lower dimensions, so we as humans can look at it and kind of understand it somehow a little bit more.
I see. Yeah, it's a challenge to do it in a useful way. I mean, basically, I mean, I don't think there are people who are really good at like visualizing more than 3 dimensions, although you end up with these mental tricks that sort of do some of it for you.
Oh yeah,
So
if you
I would
haven't
think
done
less.
it already, like go on YouTube and look for one of those videos where they have a tesseract that like is turning around, and you could stare at it for hours and it wouldn't make sense. So I'm not sure 10 dimensions would be easier.
But I think that it's, you know, it's less about projection. Well, yeah, I guess in my view, the sort of useful way of breaking it down in cases where it is useful is less, it's less about projection and more about this sort of parameterization picture. So if I can go back to this terrible cartoon I drew of, come on, of this vibration. Okay, this isn't, obviously this is not the greatest picture in the world, but you can start to get your head around it. So this is supposed to be a 4-dimensional space, and you think of it as a parameterization of 2-dimensional spaces by other 2-dimensional spaces. And I can think about 2-dimensional spaces, so I can sort of start to get my head around that. Although it may be that there's some nuance to the structure which is not illuminated by that way of thinking about it. In principle, you could try to do that all the way up, although it's going to become harder to keep it in your head and much less plausible that you're capturing the key features. But if you want to think of a 10-dimensional space, you can always, you know, that's some sort of 2-dimensional space parameterized by 2-dimensional spaces, parameterized by 2-dimensional spaces, parameterized by 2-dimensional spaces, parameterized by 2-dimensional spaces. So like you can break it down that way, but it starts to become implausible that you're getting something valuable out of it. Right. I mean, this is the value of having an actual mathematical formalism to talk about these spaces. It becomes really, really unlikely that you're going to have a useful cartoon in your head.
Yeah. Thank you. Right. Yeah, definitely to everyone listening, if you happen to check out a video of the tesseract turning around, it's mental. Okay, the other question we had is asking about quantum entanglement and how it fits into string theory.
Yeah. So I see the picture, or I see the question in the chat. I can answer the question as written in the chat more easily than I can answer the question as it was formulated. The answer to the question in the chat is yes, full stop. Definitely, I mean, quantum entanglement is really a basic feature of any quantum mechanical framework, and in string theory, things certainly are quantum mechanical. So individual strings can be in various quantum states, and therefore they can be in various superpositions of those quantum states, just like in conventional quantum mechanics. And if you have several strings, then you can build entangled states just the same way. I guess one comment I would make is that string theory, certainly sort of critical string theory, the way I've presented it, is very much intrinsically relativistic. I didn't emphasize this point, but it was sort of built into the language that I used, that it was a relativistic theory. And in quantum mechanics, once you start incorporating relativistic invariance, you're really probably supposed to be using quantum field theory instead of sort of single particle or several particle quantum mechanics. And so maybe the best analogy for sort of the framework in which to view entanglement in string theory is something closer to entanglement in quantum field theory, which is certainly a thing. But it's just a bit of a more machinery laden subject.
Yeah, thank you. Does anyone else have any questions?
I have a question, if you don't mind. So I've seen the word bosonic strings in many textbooks, and I was wondering, is it possible to have some sort of fermionic strings? I've never seen fermionic strings. I've seen superstrings and other strings, but the word fermionic strings never appeared in any kind of textbooks. Is there a reason behind that?
So indeed, superstrings are fermionic strings. So this has to do, this was all hidden in this sort of this issue of what sort of internal structure you assign to the string. I guess maybe a way to answer your question is to point out that, okay, this was a bit of a sloppy slide, but in this formulation of string theory in terms of the sort of coordinate embedding, the coordinate embeddings being fields on the string world sheet, those fields themselves are bosonic fields. And that's the bosonic of bosonic string. So it's by virtue of the fact that sort of space-time itself is comprised of ordinary sort of, the coordinates on space-time are sort of ordinary commuting, like numerical things, and not some weird Grassmann odd anti-commuting number things, that you have bosonic stuff in your string. And then you can add additional fermions on top of that, if you like. And this is what you do in the superstring. In the heterotic string, which is a phrase that appeared on one of my slides, but I didn't say the word out loud, you do frequently formalize that as having a string world sheet where you have some fermionic degrees of freedom, which are not necessarily incorporated into any super object. And so you have fermions without super. But at this point, I'm just sort of rambling about terminology. I'm not aware of a useful situation where you have purely fermionic degrees of freedom on the world sheet.
Thank you. I think that answered my question.
Cool. Any more questions?
Yeah. When you showed the compactification, where it goes from being 10-dimensional to 1 + 3-dimensional, and then the compacted dimensions, is the space that is not compacted Euclidean, and then the compactification that's where the very differential, I don't know the right word is, where the variable geometry is.
Yeah. So I had this sort of cartoon picture. Something I didn't touch on at all, which is a subject that people should care about, but I didn't have time to talk about it, is that the non-compact space that's relevant to the real world, so the world that we live in, even though in sort of first year, second year mechanics or whatever, maybe our entire undergraduate career, it's sort of modeled on Euclidean space. In the real world, we have cosmology. The universe is evolving with time in an interesting way. We live in some sort of Friedmann-Robertson-Walker metric space-time if you've taken some general relativity. And so in principle, I should be open to situations where I have a compact manifold and then I have some non-compact space, which is doing something interesting, evolving like the way that our universe actually is. And there are things that people can say about that in string theory, and then there are also challenges associated to it. But all of the things that I was talking about in particular really were restricted to some assumption that we want to work in an approximation where we ignore the cosmological evolution of our universe and we pretend that we're just living in flat Euclidean space. And indeed, in that case, in the compactification setup, you have our flat Euclidean space times some interesting small curled up structure that we don't see directly.
So although there's not a global like non-Euclidean element, the compacted geometry will handle the effects of gravity.
I'm not sure I understood exactly the question. So we're looking for, so I'm implicitly looking for, I guess, sort of what you would call vacuum solutions. So these are sort of the backgrounds against which other things should be placed on top. So my R1, 3 in this picture, this is flat Minkowski space. So spatially it's flat Euclidean space, and then the sort of time evolution is trivial. I have some interesting curled up space, and I'm going to demand that this space-time written this way, so this xn that I wrote here, secretly has to have some metric on it. I haven't defined it as a metric space because I drew a cartoon, but it's some metric space. And I'm going to need the whole thing to be a solution to Einstein's field equations. So in that sense, the whole thing needs to account for gravity by being a solution of Einstein's field equations. But then, of course, I could have extra gravitational stuff happening on top. So if this happens to describe a universe that looks something like the real world, I should be able to have like a planet sitting in my 4-dimensional space, which will have a gravitational impact, and the rest of the space-time geometry will have to accommodate. But I'm looking for sort of the empty space approximation.
That answered the question, thanks.
Awesome. Any more questions? I have one that I just have to ask. I mean, I have a list, but this is the one that I'm really curious about. So the way to kind of think about this is, so we have strings and kind of their vibrations correspond to particles that we are somewhat familiar with, right? And you at some point mentioned that you kind of get the graviton for free because it kind of pops out of the theory. The thing I'm wondering about is how you know that it's a graviton, because I can kind of understand how you would get the other particles because we kind of know what they would, what kind of properties they would have. But how would you know that something that comes out, like this particle that you find is actually a graviton? I just can't imagine what that would look like. Does that question make sense?
Yeah, that's a great question. It makes a lot of sense. There are a couple of layers of answer. The sort of cheap answer, which is the one that we usually do like in a string theory course, just where we don't have time to do everything, is that there's a slogan associated to the graviton. So we know, so if you take Einstein's equations and so there's some operations that you're supposed to do to figure out what the sort of perturbative quanta are associated to some classical field in quantum field theory. Even though the problem of quantizing gravity is challenging, we sort of, we think that we can make sense of it as what's known as an effective field theory. And in that case, you can still work out sort of what the behavior of the weakly coupled quanta of the field should be. And the graviton is supposed to be a massless spin 2 field. This is its key. So to a certain extent, this is the key property. So if you are studying some theory of if you're studying some theory of something, you invent your own thing that isn't string theory, but some other speculative theory of physics, and you're producing spectra of particles, and you produce an interacting massless spin 2 particle. If your theory is going to be a self-consistent theory, there's a good chance that what you've got your hands on is a graviton. Now, you're not actually done at that point. There are some more things that you need to check, because gravity interacts in a particular universal way with other energy and momentum. And so you need to check that the way that the graviton interacts with your other fields is the way it's supposed to. And even more, you want it to be the case that if you like have lots of gravitons that are sort of behaving coherently, that should sort of look like a gravitational background. And so it should behave as if the rest of your theory is in the presence of a classical gravitational field. And so those are some higher level checks. And indeed, these are things that you can check in the stringy construction. But the 0th order check is this massless spin 2 criterion. And when you see that, you are on track.
So I get why it wouldn't have any mass and presumably no electric charge either. Any kind of simple argument that you could make why it should be spin 2?
Well, I can do some, I mean, it would be some injustice to the careful treatment. So
all right, fair enough.
the sort of uncivilized answer is that the metric, the graviton is excitations of the metric tensor. And the metric tensor has 2 vector indices. It's G mu nu, right?
Ah.
And so in some sense, if you're going to have a field associated to it, it should be something that sort of carries 2 vector indices, which is going to look roughly like a spin 2 thing. Now that's a bad, it's bad to stop at that point, because you're really supposed to do more work, because you need to show that sort of you only get certain polarizations of those two vector indices, and there's some sort of story of decoupling of some modes because of gauge invariance. This is something. It's actually the place to look. I mean, it's the calculation that you're supposed to do is very similar to the calculation that you do to study gravitational waves in the linearized approximation. So this is, in this day and era, this is a classic calculation, because now we can measure gravitational waves with LIGO. And so everybody should go learn how to derive the form of linearized gravitational waves. And when you do that, you're also going to see this sort of massless spin 2 structure appearing, except in that case, it's sort of at the level of linearized classical wave equations. You're not necessarily treating it in a quantum mechanical framework.
Okay, I'll take that as kind of as satisfying as it's going to get, I guess, without me looking at the maths. Thank you. Okay, we have another question in the chat, and then I think we should wrap up, because we can't keep you all here forever, especially Christopher. Okay, in QFT, we say that particles are local excitations in their corresponding fields. How does that picture fit in with string theory, where each particle is a mode on separate strings? QFT, 2 electrons are excitations in the electron field. String theory, 2 electrons are modes in 2 strings. Another one that I would probably have to read several times.
Yeah, that's right? So that's also a great question. So indeed, this treatment of strings is what you might describe as a first quantized treatment of string theory, and it's the standard one. People use this phrase second quantization to refer to the way that you pass from sort of single particle quantum mechanics, or sort of fixed number of particle quantum mechanics to quantum field theory. And so you can ask about trying to second quantize this description of string theory. There's a subject called string field theory, which is a technically treacherous subject, even more so than string theory, as I've alluded to. And in that, so there are some circumstances where that's under relatively good control, although they're not the most interesting circumstances. The string field theory for the consistent superstring theories that I mentioned in the talk are not really a finished subject. But that is what that's what you would want to do, is the answer to your question. So it's a fact that we're doing some sort of first quantized treatment, and this does make you wonder if you're going to miss things. So if you try to study quantum field theory without doing quantum field theory, and only study it at the level of sort of the particle analog of what I've been doing here, then you're going to miss certain phenomena in quantum field theory, with the most obvious being what are called non-perturbative phenomena, or instantons. And there is a problem in this treatment of string theory associated with understanding phenomena that are non-perturbative in this string coupling that I mentioned, G sub S. And one big aspect of what happened in the second superstring revolution was that via indirect arguments, people were able to get some handle on how non-perturbative phenomena in the string coupling should work, without having to solve the problem of second quantizing string theory, which remains to a certain extent an open question.
Thanks again. I think that answers the question. Okay, cool. I don't think anything else came up. Thank you so much. This was a great talk. I know it's, we hope we didn't bore you in the end there. It did go on quite a bit, but I think we kind of had to make it to do it justice. Yeah. What should I say? Yes, we have another talk tomorrow on bionic hearing, which is going to be really cool. We have a professor who has personal experience with cochlear implants. He was deaf for quite a while until that restored his hearing. So he's going to talk about the physics of how they work, and a bit about his own experience with it. It's going to be very interesting. This recording will be up at some point. We're going to try to make this one go up a bit faster because we know that some people missed it. Sorry again about hitting the participant limit. And yeah, as always, our speakers are here because they want to talk about their research. So they usually won't mind if you email them about specific questions. I'm sure you'll be fine too with that. Yes, it's just a general thing. Scientists, they like their research. That's why they do it. So if you have questions, do approach people. Yeah, anything else, Amelia? Yeah.
So we normally like to ask our speakers towards the end if people who were watching this were very interested, which I'm sure everybody was since they stayed this long. What would you recommend us reading, especially string theory? A lot of the books on it are kind of popular science books. I don't know how accurate any of them are if we were actually looking to go into this field or whatever. So are there any resources or any advice you would give to people who are quite interested in this area?
You're looking for advice other than that's not in the popular science world. So there's it's a hard thing. So there's a textbook by Barton Zwiebach from MIT called, I think, A First Course in String Theory, which is definitely the gentlest introduction to the sort of machinery of string theory. There's a risk that I think is unavoidable, which is realized, in my opinion, in that book, which is just that in order to sort of make the machinery as approachable as possible without demanding that people already know quantum field theory, for example, which realistically should be a prerequisite to study string theory, you inevitably lose some of the big picture in the name of the sort of technical minutia. So I think that it's a place to get a feel for what's going on technically, but it is a challenge to really extract the whole picture from working through that textbook. And realistically, it is important to, I mean, everyone who wants to learn string theory should want to learn quantum field theory. So you should go learn quantum field theory. At least, and if you don't want to wait until you can take, a full course in quantum field theory and do all the problem sets and everything, then there's a great, I have a stronger opinion here. There's a great book by Anthony Z called Quantum Field Theory in a Nutshell. And that's not the book where you learn to be a quantum field theorist, but it's a book where you learn, roughly speaking, the right words to say in connection to quantum field theory. You sort of get the picture in your head so that then you can go take a hardcore course where you do all the scattering amplitude calculations that your professor is going to make you do. And I think that you can actually make a reasonable amount of progress by learning sort of the language in cartoons of quantum field theory at the level of Anthony Z's book, and then going and trying to read maybe some of the standard textbooks on string theory. The two standard series are the Green, Schwartz, and Witten 2 anthology books, and then the Polchinski 2 anthology books. If you ask the internet for string theory textbooks, those will be the first ones that are recommended to you.
Again, we'll put that on the page or in the YouTube description so people have that as well. Amazing. Anything else? I don't think so. Good. Well, again, thank you so much. Thank you for listening. I know a lot of people had to go at the end during the questions because we went on for very long. So thank you for everyone who stayed until the very end. And thank you so much again, Professor Beem. This was an amazing talk. And string theory is always really great when you can get it accessible because most people, haven't heard it yet.
It was a pleasure. Thanks for the invitation, and definitely thanks for everyone who held on to the end.
Amazing. Peter, I think you can end it now.
Right. Thank everybody again for coming, and I'll start my recording here.